Hello everyone. In most buildings, maintaining comfortable indoor conditions requires more than just the building envelope. That's where HVAC systems come in. HVAC stands for heating, ventilation, and air conditioning, and these systems are responsible for controlling the indoor environment so that occupants remain comfortable and healthy. Beyond simply heating or cooling the space, HVAC systems also bring fresh outdoor air into the building. This ventilation air is important because it helps dilute carbon dioxide and other pollutants that are generated by people, equipment, and building materials. Without proper ventilation, indoor air quality can quickly decline, even if the temperature itself feels comfortable. When we begin modeling buildings in OpenStudio, representing these HVAC systems accurately becomes a critical step. In fact, HVAC modeling is often one of the most complex parts of building energy simulation. Real buildings use a wide range of system types, such as packaged rooftop units, variable air volume systems, heat pumps, and many others. Each of these systems can have different components, operating strategies, and control methods. Because of this complexity, energy modelers need a clear conceptual understanding of how HVAC systems interact with the building and its thermal zones. In this chapter, we will focus on the fundamental ideas behind HVAC system modeling in OpenStudio. The goal is not just to place equipment into the model, but to understand how these systems deliver heating, cooling, and ventilation to different parts of the building and how their operation influences overall energy performance. As we discussed earlier, an OpenStudio model is organized around spaces. A space represents a physical room or area within the building and is defined by the collection of surfaces, such as walls, floors, and ceilings, and subsurfaces like windows and doors that enclose a volume of air. Each space can also include internal loads such as people, lighting, and equipment, which add heat to the environment during operation. Another important concept is the thermal zone. While spaces describe the physical layout of the building, thermal zones are used to represent how the building is conditioned by HVAC systems. A thermal zone is essentially a group of one or more spaces that are controlled together by the same HVAC system and share a common air temperature during the simulation. Because of this relationship, a thermal zone effectively includes everything inside its spaces, all the enclosing surfaces and subsurfaces, along with the internal loads that exist in those spaces. To illustrate this idea, imagine a small building that contains 4 spaces but only 2 thermal zones. One of the zones may serve just a single space, while the other zone might include the remaining 3 spaces. In practice, the spaces grouped into a thermal zone do not have to be physically next to each other, but it is generally recommended to group adjacent spaces together when possible. This usually leads to more realistic system operation and clearer model organization. During the simulation, Energy Plus performs a heat balance calculation for each thermal zone at every time step. Heat can enter or leave the zone through its surrounding surfaces depending on the thermal boundary conditions, such as outdoor weather or neighboring spaces. At the same time, internal loads inside the spaces, like occupants or equipment, add heat to the zone air. To simplify the calculations, Energy Plus assumes that the air within a thermal zone is well mixed. In other words, any heat added to the air is instantly distributed throughout the entire zone. As a result, the model assumes a uniform air temperature within the zone, meaning there are no localized hot or cold spots. Another important object in an OpenStudio model that works closely with the thermal zone is the thermostat. As we discussed earlier, a thermostat defines the target temperatures for a zone, usually through heating and cooling set points along with schedules that determine when those set points apply. The HVAC system connected to a thermal zone constantly works to bring the zone temperature toward these set points. If the zone becomes colder than the heating set point, the system provides heat. If the temperature rises above the cooling set point, the system removes heat from the zone. However, reaching the target temperature is not always instantaneous. The time it takes depends on several factors, including the capacity of the HVAC system, the size of the thermal zone, and the amount of heating or cooling load affecting that zone. If the system is too small for the space it serves, or if the building is experiencing strong external loads, such as extreme weather or solar gains, the system may struggle to reach the desired set point temperature. For this reason, careful zoning is an important part of building energy modeling. Zoning refers to the process of dividing a building into thermal zones in a way that reflects how the building will actually be conditioned. Several factors should be considered when defining zones. For example, spaces located along the building facade often experience different thermal conditions than interior spaces because they are exposed to outdoor weather and solar radiation. Similarly, some spaces may require different heating or cooling set points depending on their function or occupancy. In practice, determining the best zoning strategy is not always a purely technical calculation. It often involves a combination of engineering judgment and practical guidelines. While there are recommended rules of thumb that can help guide the process, effective zoning is partly an art, balancing model simplicity with an accurate representation of how the building operates. When a building model contains many spaces, there are often several possible ways to group those spaces into thermal zones. There is no single correct method, but engineers usually rely on a set of practical guidelines to create zones that behave realistically in the simulation. These guidelines help ensure that the assumptions used by the simulation engine, especially the assumption of well-mixed air, remain reasonable. One important factor is the similarity of exterior exposure. Spaces that have similar amounts of exterior surface area, such as walls, roofs, or windows, are often good candidates to be grouped into the same thermal zone. If two spaces are exposed to similar outdoor conditions, their thermal behavior will likely be comparable. On the other hand, if one space has many exterior walls and large windows, while another space is completely interior, their temperatures will likely respond very differently to outdoor weather. In that situation, grouping them into the same zone could produce unrealistic results. Another consideration is the timing of external loads, especially solar gains. Spaces located on the same facade often experience solar heat at similar times of the day. For example, spaces on the east side of a building receive the strongest solar radiation in the morning, while west-facing spaces experience it later in the afternoon. Spaces that experience solar gains at similar times are generally good candidates to combine into a single thermal zone. In contrast, mixing east-facing and west-facing spaces in the same zone may create conflicting load patterns. The location and connection between spaces is also important. In reality, air mixes more easily between spaces that are physically close to each other and connected by doors, corridors, or open passages. If two spaces are far apart or separated by barriers that restrict airflow, it is less realistic to assume that the air between them is well mixed. When defining thermal zones, it is helpful to think about whether air could realistically circulate between the spaces being grouped together. Space size can also influence zoning decisions. Very large spaces may not behave as a single well-mixed volume of air. For instance, in a large warehouse, air near a sun-exposed wall might become much warmer than air on the opposite side of the building. In situations like this, it can be more realistic to divide the large area into several smaller spaces and assign each one to a separate thermal zone. Another factor is the variation in internal loads. Some spaces generate much more heat than others due to equipment, lighting, or occupancy. For example, an IT or server room can have extremely high internal heat gains compared to a nearby hallway or storage area. Unless there is significant airflow connecting those spaces, their temperatures will behave quite differently. In such cases, they should typically be placed in separate thermal zones. Finally, controllability is an important consideration. Some spaces require individual temperature control because occupants need the ability to adjust their comfort conditions. A common example is hotel guest rooms, where each room typically has its own thermostat. In this situation, each room must be treated as its own thermal zone, so that the simulation can represent independent temperature control. By considering these practical guidelines, exterior exposure, timing of loads, spatial relationships, size, internal heat gains, and control requirements, you can develop a zoning strategy that better represents how the building will actually operate. In the early stages of design, after the main building envelope has been established but before detailed room layouts are created, it's often useful to run preliminary energy simulations. At this point, the goal is to evaluate general energy performance and HVAC behavior rather than exact room conditions. A common and effective practice for this phase is called core and perimeter zoning. In this method, the building is divided into separate spaces based on its facades. Each exterior facade becomes a perimeter zone, while the inner portion of the building forms the core zone. The perimeter zones typically extend about 15 to 20 feet inward from the external walls. This approach allows the modeler to capture critical differences in heating and cooling loads between the outer perimeter, where solar gains, exterior walls, and windows have major effects, and the building's core, which is more thermally stable. Core and perimeter zoning provides a realistic first approximation of how the building will behave thermally, even before interior spaces are finalized. Heating, ventilation, and air conditioning, or HVAC systems, come in a wide range of architectures, from simple standalone units to complex centralized systems. OpenStudio and Energy Plus are equipped to simulate both common configurations and advanced or unconventional designs. To make modeling more organized, OpenStudio classifies these equipments into three main categories. First, zone HVAC systems, equipment that directly serves individual thermal zones. Second, air systems or air loops, central systems that distribute conditioned air to multiple zones. Third, plant systems, systems that produce heating or cooling fluid, such as hot water or chilled water. Zone HVAC equipment represents self-contained systems designed to serve a single thermal zone. A typical example is a package terminal air conditioner, PTAC, a unit commonly found in hotel rooms or small offices, where each space needs independent climate control. Each type of zone HVAC in OpenStudio includes a predefined set of subcomponents arranged in a specific configuration. For instance, a PTAC unit generally consists of a fan, a cooling coil, and a heating coil configured to operate as an integrated system. Because these are pre-configured templates, users can only make limited modifications. You cannot, for example, simply add a backup heating coil or a humidifier unless that particular system type already allows it. Similarly, the control logic, the set of rules that determines how the system operates, is also built into the component. Although OpenStudio exposes a few parameters for adjustment, like fan control or temperature limits, the general operating behavior is fixed. The zone HVAC equipment actively monitors the set points specified by the thermostat of its thermal zone and works to maintain those target temperatures. Of course, its success depends on the equipment's capacity and the magnitude of the zone's cooling or heating loads, but the control logic is designed to follow the thermostat's commands as closely as possible. This category of HVAC equipment is particularly useful for modeling small, independently controlled spaces such as classrooms, hotel rooms, and offices, where localized comfort and straightforward system representation are key during design and simulation. Zone HVAC equipment, such as a PTAC unit, can be assigned to a thermal zone directly from the Thermal Zones tab in OpenStudio. The process is straightforward. You simply select the desired piece of zone equipment from the list and drag it onto the thermal zone you want it to serve. However, adding the equipment alone is not enough. Each thermal zone must also have a thermostat schedule that defines the heating and cooling set points over time. Without these schedules, the system does not know what temperatures it should maintain, and the equipment will not operate correctly. For that reason, thermostat schedules should also be dragged and applied to the thermal zone along with the equipment. Like most objects in OpenStudio, zone HVAC equipment has a set of properties that you can examine and modify. By clicking on the equipment in the model interface, a panel appears on the right side of the window, showing detailed information about that component. This panel displays not only the main equipment settings, but also the properties of the internal components that make up the system. For instance, a PTAC unit is actually composed of several subcomponents working together, typically a fan, a cooling coil, and a heating coil. When you inspect the PTAC in OpenStudio, you can view and adjust the parameters of each of these elements individually. Zone HVAC equipment is very useful for modeling simple systems that serve a single thermal zone. But, by design, these systems are limited. They cannot serve multiple zones, and their internal configuration cannot be extensively customized. When a project requires more flexibility, such as supplying conditioned air to several zones or designing more advanced HVAC configurations, we need to move beyond zone equipment and start working with OpenStudio air systems, which provide a much higher level of control over system design. OpenStudio can model both simple and highly complex air handling systems using what is called the air loop HVAC model. An air loop is essentially a framework that allows you to build an air system by assembling its individual components. Instead of using a pre-configured unit, you can place elements such as fans, heating coils, cooling coils, outdoor air systems, and other devices directly into the system. As the name suggests, an air loop is organized around the idea of a closed air circulation path. The system is divided into two main sections, the supply side and the demand side. On the supply side, the system conditions the air before sending it to the building. This part of the loop can include many types of equipment, such as supply fans, heating and cooling coils, heat recovery devices, and outdoor air intake systems that bring fresh air into the building. The demand side is where the system connects to the building itself. Here, thermal zones are attached to the air loop through air terminal units, which control how much conditioned air is delivered to each zone. Compared to zone HVAC equipment, air loop systems offer much greater flexibility. Because the components are assembled individually, the modeler has far more control over how the system is configured, how the equipment is arranged, and how the control strategies are defined. Another advantage is that a single air loop can serve one zone or multiple thermal zones, depending on the system design and the type of terminal units used. When modeling a system that serves only one thermal zone, modelers sometimes have two possible approaches. One option is to use an air loop, and the other is to use a predefined zone HVAC system designed for that specific situation. In many cases, both approaches can represent similar systems. Since air loops are highly configurable, they can be used to model many practical single-zone air systems. However, some single-zone systems are easier, or only possible, to represent using the dedicated zone HVAC objects that come pre-built in OpenStudio. For that reason, when a suitable zone HVAC model exists, and the system serves only one thermal zone, it is often simpler and more efficient to use the zone equipment approach. One more detail to keep in mind is how systems connect to zones. A single thermal zone can have multiple pieces of zone HVAC equipment, but it can only be connected to one air loop system. A common design strategy is to use zone equipment, such as a 4-pipe fan coil unit, to handle heating and cooling inside a zone, while using an air loop to model a dedicated outdoor air system, which supplies fresh ventilation air to the building. As you continue working with OpenStudio, these different system configurations and modeling choices will become clearer through practical examples and exercises. In many building systems, liquids are used to move heat from one place to another. This includes chilled water systems for cooling, hot water systems for heating, condenser water loops, and even domestic hot water systems. In OpenStudio, all of these liquid-based systems are modeled using the plant loop framework. Just like an air loop, a plant loop is built around the idea of a closed circulation path with two major sections, the supply side and the demand side. The supply side of a plant loop contains the equipment that either adds heat to the fluid or removes heat from it, components such as chillers, boilers, and cooling towers. These devices condition the water before it is distributed through the loop. The demand side represents the equipment that uses this conditioned water. This typically includes heating and cooling coils installed in air handling systems. Because of this, the demand side of many plant loops is connected directly to the supply side of an air loop. In other words, the plant loop conditions the water, and the air loop uses that water to condition the air. Plant loops also support a limited form of branching. On the supply side, splitters and mixers can be paired to create parallel paths, for example, to operate multiple chillers in parallel. On the demand side, a similar splitter-hand-mixer pair can be used to supply water to several loads, such as multiple heating or cooling coils connected in parallel. These branching configurations make it possible to represent many standard plant layouts. However, the Energy Plus engine does impose certain constraints. One key limitation is that a splitter cannot directly feed another splitter to create deeper sub-branches. This restriction prevents overly complex flow paths, but in practice, the branching options available in OpenStudio are sufficient for modeling the vast majority of real-world plant systems. When designing plant loops in OpenStudio, it's helpful to keep three ideas in mind. First, the distinction between supply and demand sides. Second, the use of splitters and mixers to create parallel flow paths. And third, the branching limitations imposed by the simulation engine. With these concepts in place, plant loops can be configured to represent most hydronic systems commonly found in modern buildings.